All right, let's dive right in. Today, we're tackling something absolutely massive, a potential crisis that's brewing in the heart of cosmology. The story we've been telling ourselves about the universe for decades, the one we all learned in school, well, it might be on the verge of a total revolution. So buckle up. So, just ask yourself this. What if the very foundation of how we see the cosmos is flawed? And I'm not talking about a small tweak here and there. This feels more like we're in a cosmic detective story, and our main suspect, the standard model of cosmology, is starting to show some serious cracks in its alibi. Okay, so clue number one. Astronomers are finding things out there they're calling cosmic monsters, and they've earned the name. We're talking about things like the giant arc, a structure that stretches over 3 billion light years across the sky. Now, according to our rulebook, the universe is supposed to be smooth and pretty uniform on those gigantic scales. There just hasn't been enough time since the Big Bang for gravity to pull together something that enormous. It's just impossible. It's like finding a fully built skyscraper that somehow appeared in a single day. It just shouldn't be there. Now, our second clue is, if anything, even weirder. It's got a name, the Hubble tension. And here's the problem. When we look deep into the early universe using light from right after the Big Bang, we measure one speed for its expansion. But when we look at galaxies closer to us, in the modern universe, we measure a different, faster speed. It's a flat-out contradiction. How can the universe be expanding at two different speeds at once? And this isn't some tiny measurement error, believe me. It is a deep, nagging mystery that has cosmologists absolutely stumped. So to solve these cosmic crimes, some physicists are saying, okay, we need a whole new way of thinking. We need to question the most basic thing of all, the vacuum of space itself. What if the emptiness of space isn't actually empty? And this leads us to a really radical new idea. It's called the Single Bulk Framework, or SBF for short. Now get this, it proposes that the vacuum of space is a physical, granular substance. I want you to picture a giant container filled with sand or coffee beans, packed so tightly that they're jammed, they're acting like a solid. This theory says that's what space is. It has real, tangible, mechanical properties. You have to understand, this is a huge conceptual leap. I mean, a massive one. Our standard model treats space like a passive stage. It's just an empty, boring background where the drama of physics unfolds. SBF completely flips that script. It says space is the actor. It's the active, structural material, and everything we call physics, from gravity to particles, is just the behavior of this material when it gets stressed out. Okay, so how does this wild idea of a physical granular vacuum actually help us? Let's see how this brand new clue starts to crack the case of those cosmic mysteries we started with. First up, let's go back to that maddening Hubble tension. A universe that seems to be expanding at two different speeds at the same time. How on earth does a granular vacuum make sense of that? Well, the solution comes from a really cool property of granular materials called dilatancy. It sounds complicated, but it's not. It just means they expand when you put them under stress. Think about a tightly packed bag of coffee beans. When you squeeze it, it kind of puffs out, right? That's dilatancy. SBF says space does the exact same thing. Massive objects like galaxies exert a powerful stress on the vacuum around them. This stress literally causes the granular space to expand faster in that local area. So when we measure the expansion near us, near all these galaxies, we see that faster, stress-induced rate. But the light from the early universe? That comes from a time before these giant, lumpy structures formed, a time when space was smoother and under way less stress. So naturally, we see its slower baseline expansion rate. And this just reframes the entire problem, doesn't it? SBF says the Hubble tension isn't a crisis, it's not a mistake, it's actually a successful measurement of a fundamental property of space itself, its ability to expand under stress. What looked like a baffling contradiction suddenly becomes powerful evidence for the theory. Okay, that's one mystery down. But what about the other one? Those impossibly huge cosmic monsters that break the universe's speed limit for construction. How does SBF explain those? The answer here is just so elegant. In SBF, these structures weren't built slowly, piece by piece, over billions of years. No way. Instead, they are basically fossilized structures. Think of them like stress lines or force chains that formed instantly when the entire universe jammed, when it went from a fluid-like state to its current solid-like state, right at the beginning.
The theory actually predicts that these giant structures should exist at all scales because they're literally baked into the fabric of the cosmos from day one.
So here we are. We have a theory that seems to brilliantly solve two of the biggest problems in cosmology. But now comes the most important question you can ask of any scientific theory. Can you prove it wrong? And this, right here, is where SBF really starts to shine, especially when you compare it to other big ideas like string theory. SBF isn't just a fascinating story. It makes concrete, falsifiable predictions. Predictions that we can actually test with experiments that are happening in the near future. Just take a look at this comparison. If you look at that column on the far right, falsifiability, you see the game changer. While other grand theories are basically untestable or incredibly difficult to test, SBF stands right out there with a bold strong. This theory is not afraid to put its neck on the line. And check this out, here's the roadmap for its day in court. We've got a whole series of upcoming experiments that could give us evidence for or against SBF. But the main event, the real moment of truth, is the LightBird satellite, which is set to launch in the early 2030s. It will be looking for a very, very specific sawtooth pattern in the light from the early universe. If that pattern is there, it is the smoking gun for SBF. If it's not, well, the theory is in some serious trouble. It's high-stakes science, and it's happening in our lifetime. So, let's just imagine for a second. What if LightBird finds that sawtooth pattern? What if SBF is correct? This isn't just about a new chapter in a physics textbook. This would fundamentally change our entire picture of reality itself. I mean, think about it. If this theory holds up, space is a real physical thing. Particles like electrons aren't fundamental little points anymore. They're more like complicated knots or defects in the very structure of space. Forces aren't carried by mysterious particles. They're just patterns of stress moving through this cosmic material. The universe in this picture is less of a magic show and a whole lot more like a giant, intricate machine. It all comes down to this one profound shift in thinking. We would go from seeing space as the passive stage where reality happens to understanding that space is reality. It's the one and only actor on the stage, and everything else we see is just a consequence of its performance. And that leaves us with one final, totally mind-bending question to chew on. If the vacuum of space is a tangible, physical material, then what does that make us? What are we, as beings made of particles that are just knots in this substance as we move through it? It's a thought that really, truly redefines our place in the cosmos.